must also be equal to 180. So let's make this angle the subject and substitute it into equation 3. So angle DEF is equal to 180 minus 8. Akofala, are you there?
Yes, please.
So if angle DEF is equal to 180 minus 8, substitute, so this is 4. Adelaide, are you there? Adelaide is going to close the lid. So substitute equation 4 into equation 3. Okay, so the substitution is clear. So 180 minus A plus R1 plus R2 must be equal to 180. Therefore, hold on. Okay. Therefore, we can conclude that A is equal to R1 plus R2. And this is a very important formula. So, we could get this because of the fact that we joined the two normals.
Yes, please.
So what this formula means is that the sum of the two refractions, R1 and R2, is equal to, so you can be given a question where you have R1 and R2. Then we can ask you to find A, and this formula would help you out. Okay? Or when you have A and you have one of them, you can also use the formula to find the other ones. Please, are we fine? Are we fine? Hey, so you won't talk? Oh?
Yes,
Okay.
please.
Then let me move on. We got the total deviation to be equal to sigma 1 plus sigma 2. Sigma 1, we got I minus R1 plus, here we got E minus R2. And if you recall, we got I plus E minus R1 plus R2. And because we have a relation for this, then we can say that the total deviation is also equal to I plus E minus A. So beautifully. Please, do we follow?
I don't understand the sigma parts.
Oh, because you went off.
No, I didn't go off. I was following, but I don't understand it.
You see, this whole angle here. This whole angle. The angle of incidence is equal to this angle, isn't it? Marvelous, isn't it?
Yes.
So if I is equal to the first deviation, sigma 1, plus the angle of refraction there. Marvelous, make sigma 1 the subject.
I minus R.
Then E is also equal to this. E is equal to R2 plus sigma 2. Marvelous. Make sigma 2 the subject.
E minus R2.
Then we said that total deviation, which is this, is equal to sigma 1 plus sigma 2. So put whatever you got for sigma 1 and 2 into it. And you get this. You get this relation. Then, because we've proven that A is this, you put this in. Are you okay?
Yes, please. Thank you.
All right. Then another thing. You see, the deviation within, the deviation which occurs at the first plane AB and the second plane AC depends on three main factors. Can I clean this side? If you have put down the equation, can I clean it?
Yes.
So the deviation at the first plane and then the second plane depends on three main factors. The factors on which the deviation depends on are: one, the angle of incidence. Because look at something. Because the light is traveling from air to glass, it will always bend towards the normal. Now, if I'm gradually increasing the angle of incidence here, what do you think will happen to the deviation? Will it increase or decrease? If I'm gradually increasing the angle of incidence from a very small value and I progressively increases it, will the deviation at the first plane AB increase or decrease?
I think it will decrease.
It will decrease. Okay. Now, when it's deviating or when it's decreasing, because it will decrease because it will still be, the refracted ray will be shifting towards the normal. So it will decrease. So when this is changing, it would affect sigma 1 and also would affect sigma 2. Please, are we okay? So the deviation within the block depends on the angle of incidence. 2, it will also depend on the wavelength of the incident light. Wavelength of the incident light. And this, it means that different lights have different wavelengths. Red light has its own wavelength, blue, indigo, violet, and so different lights have different wavelengths. So when you change the incident light, it would also affect the deviation. Then the third factor on which the deviation depends on is the refractive index of the material. We have different glasses: crown glass, perspex, okay, plastic glasses, and so on and so forth. So when you vary the material, it will also affect the deviation. So the deviation also depends on the refractive index of the material used as glass block. Let me put it. Of the material used as a prism. So these are the factors on which the deviation, the total deviation, actually depends on. Please, class, are we okay? Are we okay?
Yes, please.
All right. Now, when you are in the lab conducting experiments, the only factor on which you have a control on is the first one.
Mr. Edia, please, the third point, is it refractive index?
Refractive. Okay. I'm tired. So refractive index of the material used as a prism. So when you are in the lab doing the experiment, okay, the only factor on which you have a control on is I. You can't control the wavelength of the light. Maybe we are using the sunlight. Who is Mr. Edia to control the wavelength of the sunlight? Okay. And who is Akofala to do that? Then, so long as I'm given a particular prism, I have no control over the refractive index. It is still what it is. But I can change the angle of incidence. For that, I have control on. Please, are we okay? Are we okay?
Yes,
Good.
please.
So, for the sake of practicals, we will close our eyes to the two and only talk about the one. But please put it at the back of your head that these are the factors on which the deviation actually depends on. Now, during experiments, we may decide to be increasing the angle of incidence, increasing the angle of incidence progressively, or gradually, okay? Maybe from a small value, then we increase it bit by bit. So if we are progressively increasing the angle of incidence, what do you think will be happening to the angle of deviation?
It will be decreasing.
Good. It will be decreasing. Is a Dubia here? Oh, Dubia, you've gone to sleep.
Yes, please.
Okay. Hey. Okay. Hello.
Mr. Edia, please, can you please explain why the deviation will be decreasing?
Oh, Anita. Okay, Dubia, Nana Jemfa, explain to us why you think that angle of deviation will be decreasing.
Mr. Edia, please, honestly, I just feel like it will be decreasing.
Hey.
Mr. Edia, please, this is because
more views. Let's say ideas.
Is it because it approaches the normal?
Exactly. Because you see, and that's the fact. There's it. There's the normal N1. But the point is that because light is traveling from a less dense medium into a denser medium, okay, it will always be deviating towards the normal. So if this is it, if you are starting with this, let's assume this is it. When you increase this, it will further be deviating towards the normal. Increase it, it will always be deviating towards the normal, and therefore will be closing the gap between the refracted ray and the normal. Anita, are you okay? Hello,
yes,
Anita, are you okay?
yes.
So that is the reason. That's the reason. Okay.
Yes, please.
So as we progressively increases the angle of incidence, okay, the angle of deviation sigma would also be decreasing. Now it will come to a point where the angle of deviation will not decrease. So there will be a minimum value of the angle of deviation as we increase the angle of incidence. So yes, as we increase the angle of incidence, okay, the deviation will be reducing it to a point. Then the trend will change. Okay, as we continue to increase, a time will come where it will not increase again. The angle of deviation will not decrease again, but it will start to decrease. It will start to increase rather. Moving away from the norm. The norm is that as we increase the angle of incidence, the angle of deviation must be decreasing. So it would obey, but it will do so up to a certain limit. Then after that limit, any increase in the angle of incidence would cause an increase rather in the angle of deviation. Are we okay? Now, something so interesting happens or will happen at the minimum angle of deviation. And the minimum angle of deviation is that least value of angle of deviation as a result of us increasing the angle of incidence. Okay, it is from that minimum value, then the deviation begins to increase instead of decreasing. Please, are you okay here? Are you okay?
Yes, please.
So at the minimum deviation, this is what will happen. At the minimum deviation, we realize that the refracted ray, okay, passes through the glass prism symmetrically. At the minimum deviation, the refracted ray passes through the prism, the triangular prism, symmetrically. And then two, the same refracted ray, is then parallel to the base of the prism. It's parallel to the base of the triangular prism. So theoretically, these are what happens at the minimum deviation. At that least value of deviation, we said that the refracted ray passes through the glass triangular prism symmetrically. Symmetrical means that it divides the prism into two equal parts. As I don't mean breaking it into, but it's like dividing it. Okay. Then this refracted ray is parallel, directly parallel to the base of it. Please, are we okay with the condition at the minimum deviation? Are we okay?
Yes.
Yes, please.
Furthermore, at the minimum deviation, the angle of incidence is equal to the angle of emergence. So at the minimum deviation, I is equal to E. So if I, at the minimum deviation, if I is 30, E would also be 30. And this is what we saw under refraction in rectangular prism. But here it will occur at the minimum deviation. Then at the same minimum deviation, R1 is equal to R2. So conditions, at the minimum deviation, the ray passes through the glass prism symmetrically, and the refracted ray is parallel to the base of the prism. At the minimum deviation, angle of incidence equals the angle of emergence. And then the angle of refraction R1 at the first plane is equal to the angle of refraction at the second plane. R1 is equal to R2. And these are what happens. And this explains the first part of that symmetrical thing we're talking about. The ray passing it through symmetrically. So in that case, what will be the nature of the total deviation? The total deviation sigma we saw to be equal to I plus E minus R1 plus R2, which we said this is equal to A. This is equal to A. So this is A. Now, so sigma, the total deviation at the minimum, at the least, or the minimum deviation, or what happens to the total deviation as we reach the least or the minimum deviation. That's why I brought M here. We are saying that at the minimum deviation, I is equal to E. Okay, so if I is equal to E, then E is simply equal to I. So we have, instead of E here, let's put, okay, let me maintain this, and then I plus I minus E. Please, are we okay? Are we okay with this? Are we okay with this?
Yes, please.
So this is 2I minus A. Let's make I the subject. I therefore would be equal to the minimum deviation plus A over 2. Okay, 2. We are also saying that at the minimum deviation, R1 is equal to R2. If R1 is equal to R2, then we can equate this to be simply R, meaning we don't have 1, we don't have 2. They are all equal to the angle of refraction 1. So using A is equal to R1 plus R2, we can also say that A is equal to R plus R. Therefore, we have 2R. Therefore, the angle of refraction is equal to A over 2. A over 2. Now we can use this condition to find an expression for determining the refractive index of the glass block. We know absolute refractive index from Snell's law. N is equal to sine I over sine r. We have had our I to be this. So sine of sigma m plus a over 2 divided by sine r. R is this. So a over 2. And this is how to determine the refractive index of this glass block, okay, as we attain the minimum deviation. So this is the expression for the refractive index of the glass block as at the minimum deviation. And please, this is a very important formula we'll be using in refraction in triangular prism. So, but it's proving to, you have to also understand. So go through it and ask questions so I can explain. I'm giving you time to write. We have 9 minutes. Please, all those you see, look at the derivations or equations we've been deriving from refraction and rectangular prism. Okay, apparent what they saying, the apparent depth and then the real depth, and then this. Please spend time to be reviewing it at your own. Don't just look at it and then you learn the formula. Go through it, because if you do that, when a question is twisted, then you can at any time apply and then use it. Is that okay?
Miss Ada,
Hello.
please, is this formula only used for triangular prism?
Yes.
Okay. Thank you.
And it is only used at the for minimum, at the attainment of minimum deviation, where we increase the angle of incidence bit by bit, okay, and expecting the refracted the angle of refraction or deviation to also be decreasing, the angle
Yes,
of
please.
deviation to be decreasing, but it will only do that to a certain point.
Yes,
It will
Miss
only do
Ada,
that. Hello.
please, the A, does it stand for the point or the angle?
A is the angle of the prism. Angle of
Okay.
the prism, yes. That's why I brought it within. That's why I brought it here. Are you
Mr.
okay?
Idria,
Hello.
Mr. Idria, please can you go over again?
Yeah, you have 7 minutes. Oh. Yeah. Okay, let's quickly go over. Hey, Eliana doesn't talk. Oh. Eliana is quiet. So let's go over it for the last time. So we are gradually increasing the angle of incidence. So as we increase the angle of incidence, okay, gradually, we get that decreasing angle. Okay. Now, the angle of deviation would also decrease, okay, to a certain point as you increase the angle of incidence. Now, it will come to a point where as we increase the angle of incidence, the angle of deviation will not decrease, but it would rather increase. So we are looking at what happens at that minimum value of the angle of deviation. So we are determining it at the minimum deviation, what happens? Because the trend is that it is decreasing. But it will come to a point where it will not decrease again. So what happens at that least value, minimal value of the deviation, which we are calling as sigma m? Now, at the minimum deviation, the refracted ray passes through the glass prism symmetrically. So it's like partitioning the whole prism into two. So this is the first thing which happens, and then the refracted ray also moves parallel to the base. Okay. Now, apart from this two, what we also realize is that at the minimum deviation, the angle of incidence is equal to the angle of emergence. Adu, are you there? So angle of incidence
Yes,
I
please.
equals the angle of emergence. 2, the angle of refraction R1 is equal to the angle of refraction R2. So since they are all equal, then we can only say that, oh, I is equal to E, and they are all equal to I. Then R1 is equal to R2, and they are all equal to R, because there's no distinction. They are the same, so there's no need of 1, 1, and then E. They are all the same. That's why I've created this, okay? Then we got the total or maximum deviation, okay, which we obtained from sigma 1 plus sigma 2 to be equal to I plus E minus A. Now we are saying that at the minimum deviation, okay, so we are not looking at the total deviation before, but we are looking at what happens at the minimum deviation. That's why we've brought M to this consideration, meaning that if we haven't attained the minimum deviation, please just still holds that total deviation will be equal to this. Are we okay? Okay. But the moment we attain total minimum deviation, then you have to bring it, because it's the least deviation, you have to bring M to this to distinguish it from this situation. Now, at this condition, I is equal to E, and they are all equal. So in place of E, we can bring just another I to have 2I plus A. Let's make I the subject. So we have I being equal to, oh, sorry, it's not plus, minus. I equal to sigma M plus E, all divided by 2. Marvelous, are you fine?
Yes, please.
Then we also earlier said that A is equal to R1 plus R2. And at the minimum deviation, there's no R1, there's no R2. They are all equal to R. So this is 2R. Therefore, R will be equal to A over 2. Let's substitute. Then we know that their absolute refractive index is equal to sine I over sine R. But we can also express this same refractive index in terms of what happens at minimum deviation. So, but it wouldn't, this expressing the refractive index, okay, at the condition where minimum deviation takes place, please doesn't change the refractive index of the glass block. But all that we are saying is that we can also determine the refractive index of the glass block using that condition of minimum deviation. Okay, so N is still this, but it's also can be obtained at using the condition of minimum deviation, which is sigma M plus A over 2 divided by sine A over 2. Meaning that whether it is this before, if it's not at minimum deviation, or at this same value, this value must be the same. That's all that I'm saying. Please, are we okay?
Yes, please.
All right. I think our time is up. Oh, 9:01. So we'll end here. We'll end here, okay? And then next week, I think we are left with lenses and total internal reflection to finish light. Then we can be smiling to the bank. So this is why I draw the curtains on today's meeting. Please, bye-bye. See you next week,
Bye.
okay?
Bye.
Okay.